Hi everyone, I'm Dylan Slogrove from MWR Cybersecurity, a South African cybersecurity consultancy, and today we're going to be walking through TryHackme's Advent of Cyber Day 8. So apparently this one is about smart contracts. I must admit, I don't really know very much about smart contracts, so I'm going to be learning along with you all. So look forward to it. Let's kick off. Right. After it was discovered that Best Festival Company was now on the blockchain and attempting to mint their cryptocurrency, they were quickly compromised. Best Festival Company lost all its currency in the exchange because of the attack. It is up to you as a red team operator to discover how the attacker exploited the contract and attempt to recreate the attack against the same target contract. Right. So what are we going to learn today? Going to explain what smart contracts are, how they relate to the blockchain, and why they're important. We're going to understand how contracts are related, what they're built upon, and their standard core functions, and we're going to understand and exploit a common smart contract vulnerability. Right, what is a blockchain? One of the most recently innovated and discussed technologies is the blockchain and its impact on modern computing. While historically it's been used as a financial technology, it's recently expanded into many other industries and applications. Informally, a blockchain acts as a database to store information in a specified format and is shared among members of a network with no single entity. By definition, a blockchain is a digital database or ledger distributed among nodes of a peer-to-peer network. Blockchain is distributed among peers or members, no central servers, hence it being called decentralized. Due to its decentralized nature, each peer is expected to maintain the integrity of the blockchain. If one member of the network attempted to modify a blockchain maliciously, other members would compare it to their blockchain for integrity and determine if the whole network should express that change. The core blockchain technology aims to be decentralized and maintain integrity. Cryptography is employed to negotiate transactions and provide utility to the blockchain. What does this mean for security? We ignore the core blockchain technology itself, which relies on cryptography, and instead focus on how data is transferred and negotiated. We may find the answer concerning. Throughout this task... Sorry, I have a visitor. Everyone say hello to Diablo. Right, but what does this mean for security? If we ignore the core blockchain technology itself, relies on cryptography, and instead focus on how data is transferred and negotiated, we may find the answer concerning. Throughout this task, we will continue to investigate the security of how information is communicated throughout the blockchain and observe real-world examples of practical applications of blockchain. Right. A majority of practical applications of blockchain rely on a technology known as a smart contract. Smart contracts are most commonly used as the backbone of DeFi applications, that's decentralized finance, to support a cryptocurrency on a blockchain. DeFi applications facilitate currency exchange between entities. A smart contract defines the details of the exchange. A smart contract is a program stored on a blockchain that runs when predetermined conditions are met. Smart contracts are very comparable to any other program created from a scripting language. Several languages, such as Solidarity, Viper, and Yule, have been developed to facilitate the creation of contracts. Smart contracts can even be developed using traditional programming languages such as Rust and JavaScript. At its core, smart contracts wait for conditions and execute actions, similar to traditional logic. Right. Building a smart contract may seem intimidating, but it greatly contrasts with core object-oriented programming concepts. Before diving deeper into a contract's functionality, let's imagine a contract was a class. Depending on the fields or information stored in a class, you may want individual fields to be private, preventing access or modifications unless conditions are met. A smart contract's fields or information should be private and only accessed or modified from functions defined in the contract. A contract commonly has several functions that act similarly to accessors and mutators, such as checking the balance, depositing, and withdrawing currency. Once a contract is deployed on a blockchain, another contract can then use its functions to call or execute the functions we just defined above. If we controlled contract A, and contract B wanted to first deposit 1 Ethereum and then withdraw 1 Ethereum from contract A, contract B calls the deposit function of contract A. Contract A authorizes the deposit after checking if any predetermined conditions are met. As you can see in this little diagram here. Contract B calls the withdraw function of contract A. Contract A authorizes the deposit if the predetermined conditions for withdrawal are met. Contract B can execute other functions after the ether is sent from contract A, but before the function resolves. I assume this is going to be on the Ethereum blockchain. Right. How do vulnerabilities in smart contracts occur? Most smart contract vulnerabilities arise due to logic issues or poor exception handling. Most vulnerabilities arise in functions when conditions are insecurely implemented through the previously mentioned issues. Let's take a step back to contract A in the previous section. The conditions of the withdrawal function are: the balance is greater than 0, send Ethereum. At first glance, this may seem fine, but when is the amount to be sent subtracted from the balance? Referring back to the contract diagram, it is only ever deducted from the balance after the Ethereum is sent. Is this an issue? The function should finish before the contract can process any other functions. But if you recall, the contract can consecutively make new calls to a function while an old function is still executing. An attacker can continuously attempt to call the withdrawal function before it can clear the balance. It means that the predefined conditions will always be met. A developer must modify the function's logic to remove the balance before another call can be made, or require stricter requirements to be met. In the above section, we informally introduced a common vulnerability known as re-entrancy. Reiterating what was covered above, a re-entrancy occurs when a malicious contract uses a fallback function to continue depleting a contract's total balance due to flawed logic after an initial withdrawal function occurs. We have broken up the attack into diagrams similar to those previously seen. Better. Let's assume that contract B is the attacking contract and contract A is the storage contract. Contract B will execute a function to deposit, then withdraw at least one ether. This process is required to initiate the withdrawal function's response. Note the difference between account balance and total balance in the above diagram. The storage contract separates balances per account, each account's total balance combined. We are specifically targeting the total balance we do not own to exploit the contract. I'll give you a second to go to look at these lovely diagrams. Right. At this point, contract B can either drop the response from a withdrawal function or invoke a fallback function. A fallback function is a reserved function in Solidity that can appear once in a single contract. The function is executed when currency is sent with no other context or data. For example, what is happening in this example? The fallback function calls the withdrawal function again, while the original call to the function was never fully resolved. Remember, balance is never set back to 0, and the contract thinks of ether as its total balance when sending it, not divided into each account, so it will continue to send currency beyond the account's balance until the total balance is 0. Because the withdrawal function sends ether with no context or data, the fallback function will be called again, and thus an infinite loop can now occur. Now that we've covered how this vulnerability occurs and how we can exploit it, let's put it to the test. We have provided you with a contract deployed by Best Festival Company in a safe and controlled environment that allows you to deploy contracts as if they were on a public blockchain. Right, for this practical section, I've never done this before. I've never done attacks on smart contracts before. Yes, let's get into it. Let's try our hand at actively exploiting a contract prone to a re-entrancy vulnerability. For this task, we will use Remix IDE, which offers a safe and controlled environment to test and deploy contracts as if they were on a public blockchain. Download the zip folder attached to this task and open Remix in your preferred browser. We have provided you with two files. One gathered from the Best Festival Company used to host their cryptocurrency balance, and another malicious contract that will attempt to exploit the re-entrancy vulnerability. Both contracts are legitimate Solidity contracts, but no need to worry if you need help understanding the program syntax behind each. They follow the same functionality and methodology we covered throughout this task, just translated to code. Right, let's get familiar with the Remix environment. When you first open Remix, you want to draw your attention to the left side. There will be a File Explorer, Search, Solidity Compiler, and Deployment Navigation button respectively, from top to bottom. We will spend most of our time in the Deploy and Run Transactions menu, as it allows us to select from an environment, account, and contract, and interact with the contracts we have compiled. To get started with the task, you will need to import the task files provided to you. To do this, navigate to File Explorer, Default Workspace, and load a local file into the current workspace. From here, you can select the necessary sol file to be imported. we've provided you with an etherstore.sol and attack.sol file that functions as we introduced in this section. Alrighty, let's go do that. We are in Files, Default Workspace, Load a local file. And we can just select these, and we click on them and it opens them in E. Right, the next step is to compile the contracts, navigate to the Solidity compiler, and select 0.8.10 plus commit and a commit number from the drop-down compiler menu. Now you can compile the contract by pressing the compile button. You can ignore any warnings you may receive when compiling. Right, let's do that. Compile. There we go. And now we compile our attack. Great. Now that we have the contracts compiled, they are ready to be deployed from the Deployment tab. To the right is a screenshot of the Deployment tab and labels that we will use to reference menu elements as we move throughout the deployment process. First, we must select a contract for deployment from the contract dropdown, label 6. We should deploy the EtherStore contract or target contract to begin. For deployment, you only need to press the deploy button. Right, let's deploy ourselves a contract. And deploy our EtherStore contract. Go. We can now interact with the contract underneath the Deployed Contracts subsection. To test the contract, we can deposit Ether into the contract to be added to the total balance. To deposit, insert a value in the value text box and select the currency denomination at the dropdown under label 5. Once setup is complete, you can deposit by pressing the deposit button. Alright, let's do that. We're going to be depositing Ether. Let's go with 10 Ether. And let us, here we can interact with the deployed contract. We can deposit our 10 Ether. As you see, that successfully worked. Have a balance of 10 Ether. Note, when pressing the deposit button, this is a public function we are calling just as if it were another contract calling the function externally. We've now successfully deployed our first contract and used it. You should see the balance update. Already done that. Now that we have deployed our first contract, switch to a different account and repeat the same process. This time you'll be exploiting the original contract and should see the exploit actively occur. We've provided a summary of the steps to deploy and interact with the contract below. Right, step 1. Select the contract you want to deploy from the contract drop-down menu under label 6. Okay, let us first switch accounts to our attacker account, and we pick our attacker contract. Deploy the contract by pressing the deploy button. Note, you need to provide a reference to the contract you are targeting before deploying the attacker contract. To accomplish this, copy the address for EtherStore from label 11 and paste the value in the text box under label 8. Right, we can copy our address, paste it, and we can deploy. And there we go. That works. Confirm that the contract was deployed and the attack function can be seen from the deployed contracts subsection. There we go. We have an attack function. Execute and or interact with the contracts function. Note that most functions require some form of value input to execute a function properly. Alright, let's do that. Try for 1 Ether and attack. Soon, our attack will be successful. We'll have a bunch of Ether. There we go. We have a balance of 11 Ether. Alright, if you get stuck, reread through the discovery and explanation of the re-entrancy vulnerability. Recall that it must first deposit and withdraw before the fallback function can occur. Alright, if not already completed, download the zip folder attached to the start and open Remix in your preferred browser. We've already done that. What flag is found after attacking the provided EtherStore contract? Well, we have our flag here. And we can paste that in. Submit. Answer's incorrect. Well, that's not right. Huh. Must be a bug. But regardless, we have our flag. Are you up for a little challenge to celebrate day 8? Try your hands at these easy challenge rules: Quotient, and Agent T. Well, I hope you've all had a good time learning how to attack smart contracts. I hope that you enjoy the rest of your time with the TryHackme Advent of Cyber Challenge, and with TryHackme rooms in general. Thanks for watching.